All right, let's finish the limits test review, chapter 1. This is the back page. Uh, these are multiple choice questions here. Evaluate the limit if it exists. So the first thing we do, if we're evaluating a limit algebraically, we just plug in the x value and see if that gives us a real number. If that gives us a real number, then we're done. That's our answer. So in this case, if we plug in 2, we get 4 plus 2, which is 6 minus 6 is 0. Denominator also gives us 0. So 0 over 0 indeterminate form tells us that there's more work that needs to be done. There's a hole in this graph that's preventing us to evaluate the limit cleanly. So we have to find a way to cancel out some common factors. So in this case, if we factor the numerator, we get x plus 3 times x minus 2. And then the denominator, the 2 minus x, we see there's commonality between 2 minus x and x minus 2, but it's not quite the same. So what we can do is, what if we factored out a negative 1? Then if we factor out a negative 1, then the signs will change and we get x minus 2 from 2 minus x. And now we can cancel out the x minus 2's. Now that's a match. And then the resulting expression is x plus 3 over negative 1. Once we factor out the denominator that's causing the 0 over 0, then we can reevaluate the limits. Plug 2 in for x, we get 2 plus 3. Don't forget the negative 1, so 5 over negative 1 is negative 5. Okay, number 2, evaluate the limit if it exists. If we plug in 9, we get 9 minus 5 is 4. Root 4 is 2. 2 minus 2 is 0. Denominator also gives 0. We have another indeterminate form. Now these are special types of problems where the way we evaluate is we multiply by the conjugate. Usually in previous courses you may have seen where you had to rationalize the denominator, multiplying by the conjugate, but in this case we're multiplying by the conjugate of the numerator to help us simplify and identify the whole or the common expression that we can take out between the numerator and denominator. So in this case, we multiply by the conjugate. The conjugate of the numerator is simply taking, we'll keep the exact same terms, the root x minus 5 and the 2, but we just change the signs. So from a negative, we change to a plus, and then we multiply. We essentially are multiplying by 1. So we want the numerator and denominator to be the same expression. So if we expand this out, the first terms gives us x minus 5. The outer terms, inside and outer terms will cancel out. And then negative 2 times positive 2 is negative 4. We get x minus 9. X minus 9 will cancel out with the expression in the denominator. We're left with 1 over the square root of x minus 5 plus 2. Now that the x minus 9 has been canceled out and taken care of, we can reevaluate the expression. Plug 9 into the remaining expression. We get root 9 minus 5, which is 4. Root 4 is 2. 2 plus 2 is 4, so 1 over 4. Okay, next one here. Complex fraction. First thing we do, plug in our target x value. So plug 2 in for x, we get 1/2 minus 1/2 is 0. 2 minus 2 is 0 in indeterminate form. So with complex fractions here, what we want to do is try and, here in this case, we're going to find a common denominator, and then we're going to reduce the this complex fraction and see if from there we can identify terms to cancel out. So first, I'm going to find a common denominator for this top portion. So the top portion here, x and 2, the common denominator will be 2x. I balance the numerator and denominator. So, balance the numerator, so I get 2 over 2x minus x over 2x. Combine that to be one fraction, 2 minus x over 2x, all over x minus 2. We're going to resolve this complex fraction. Multiplying by the reciprocal of the x minus 2, I can bring that up as 1 over x minus 2. And then once I have that, we get 2 minus x over 2x times 1 over x minus 2. The 2 minus x and x minus 2 are they're off by a factor of -1. So if we factor out a -1, we can get the numerator and denominator to match, cancel out. We're left with -1 over 2x. Plug 2 into the remaining x value, we get -1 over 4. Okay, the next problem here, we have a piecewise function. However, just like the first page, or from the first page of the review, we see that the branches from the left side of -3 and from the right side of -3 are all self-contained within this piecewise function. So it says find the k value where will cause this function to be continuous. Okay, first thing is we don't know exactly where the order pair is. What we can do is skip down to the second condition and see if the limit exists. So does and then we want where the limit exists to agree where the order pair exists. So if we find out where the limit exists, then we can use that to help us guide where we want k to be so that the hole is filled. All right, so we can factor the numerator here. 2x squared plus 5x minus 3. We factor out to be 2x minus 1 times x plus 3. X squared minus 9, difference of squares. We can factor that out to be x plus 3 and x minus 3. Cancel out the x plus 3's. We're left with 2x minus 1 over x minus 3. Reevaluate the limits. We get -6 minus 1 over -3 minus 3. -7 over -6 is 7/6. So 7/6 is the y value where the graph will meet on both sides of -3. But there's a hole in the graph. So that hole in the graph exists at 7/6. So that we can just replace k with 7/6 to allow that hole to be filled in. Number 5, the function is shown on the graph and the form g of x is given. And the graph g of x is given, which of the following could be the value of the constants a and b. All right, so a couple of things to note. If we want to find a and b, what we can do is we can set numerator and denominator equal to 0, and then we can use the graph to help us through with that, to fill in information that's relevant. So just as a reminder here, okay, whenever we set the numerator of a function equal to 0, of a rational function equal to 0, the results will be x-intercepts. So if we set the numerator equal to 0, if we solve for x, we're going to find x-intercepts. If we set the denominator equal to 0, then that's going to be where the graph is undefined. We use that to find vertical asymptotes and maybe even holes as well, but basically where the graph is undefined. All right, so if we look at our graph and if we identify where the x-intercepts and the vertical asymptotes are, we see the x-intercepts will be at -2 and 2. We see the vertical asymptotes will be at x equals -1 and x equals 1. Okay, so we can use that to help us. If we set the numerator of the g of x equal to 0, x squared plus a is equal to 0. So we know the x-intercepts will occur at x equals 2 because 2 and -2 because that's what we see. So if we plug in 2 in for x, we get 2 squared, which is 4. 4 plus a is 0, so a equals -4. If we do the same thing for the other x-intercept, which is -2, we also will get -2 squared, which is 4. A is equal to -4. So both 2 and -2 x-intercepts will give us the same a value. And when we set the denominator equal to 0, the bx squared minus 3 equal to 0. If we set that equal to 0, then the result of that will be the vertical asymptotes. We know the vertical asymptotes by looking at the graph, which is at -1 and 1. So if we plug 1 in for x, we get b times 1 squared, which is b minus 3, which is equal to b equals 3. If I plug in x equals -1, I get the same result. -1 squared will still give us +1 times b, which is b minus 3. So we get b equals 3. So a equals -4 and b equals 3. Replace that into our expression. We get x squared minus 4 and 3x squared minus 3. Okay, last one here, identify the vertical asymptotes. Vertical asymptotes, we simply set the denominator equal to 0, which is x minus 1 and x plus 2. However, a little misleading here. This x minus 1 we see is a factor in the denominator. However, it does cancel out with a factor in the numerator. So the x equals this x minus 1 is actually representative of not a vertical asymptote, but rather a hole in the graph. So if we factor the numerator, we get x minus 1 times x plus 4. The x minus 1 cancels out. This is actually a x-intercept. The only vertical asymptote that we have is at x equals -2 by setting x plus 2 equal to 0.